Swayam Prabha. Digital India. Educated India.
Now, if I remember right, this was the equation we had. T So, we were looking at the solution to this problem, okay. That is, you have a base flow which is laminar, on top of that you have the periodic pressure drop. So, we split the problem into two parts, and we looked at the base flow solution which gave the laminar profile. Now, we are looking at the periodic part and trying to understand how this periodic part can be analyzed. There was one dimensionless number Rw which we came up with, which is the Strouhal number, which is r squared omega by nu, okay. And this is something which can be viewed as the ratio of two time scales, and depending on large Strouhal number or low Strouhal number, you have an understanding of the process. So, low Strouhal number means the frequency is low, okay, and the large Strouhal number means the opposite of that. So, this is the frequency of the periodic oscillation, and the reciprocal of that is the time scale, and r by nu is the momentum diffusive time scale, r squared by nu. This also has units of time. So, this is time for momentum diffusivity divided by time of oscillation. Okay. So, that is the thing we discussed. We analyze the problem by rescaling this in the limit of low Strouhal number, but we want to understand what is happening for the general case. For low Strouhal number, the frequency of the pressure variation is very slow, the frequency is very low, okay. And what that means is the momentum diffusivity has enough time, the momentum has enough diffusivity to diffuse through and catch up with the pressure fluctuation, and the velocity and the pressure are in phase, okay. So, for low Rw, velocity and pressure are in phase. Now, what we want to do is we want to analyze the general case where Rw is not very low, okay. And how did we get this insight? By doing some rescaling. Rw was multiplying the time derivative term, and we said for low Rw the time derivative can be neglected, and that is the, I can do that as long as all these terms, the du by dt, the second derivative here, they are all of the same order of magnitude, okay. An implicit understanding when I am doing dimensionless analysis is that all these derivatives are all of the same order, okay. Then the parameter which is multiplying that term gives you an idea of how significant that term is, okay. So, when I neglected the time derivative term, idea was the time derivative term in dimensionless form and this spatial derivative were of the same order of magnitude. So, because this was multiplied by Rw which was very small, I could neglect it, okay. Rw could be small, if du by dt is large, I can't neglect because that can be a significant contribution. So, there is an underlying assumption we make, the whole philosophy of making things dimensional is this: all these variables, all these derivatives all have to have the same order of magnitude, okay. Just keep that in mind. Okay, now let us proceed to solve this problem, which is again a dimensionless equation. The way I have written it is dimensionless, okay, and all these variables t used all are dimensionless. So, if we seek uz of r comma t as sin rw t plus no, sorry, sin rw t multiplied by h of r. So, this is r squared multiplied by omega divided by nu, and this is r subscript omega, which is the Strouhal number, okay. So, I mean there is some, so this is the Strouhal number. You substitute it here, what we get is cosine rwt multiplied by h of r equals sin rwt plus 1 by r d by dr of r dx by dr times sin rwt. This is what we got, okay. And what you see is that the time dependent trigonometric terms are not cancelling off, because I have cosine here, I have sine here, okay. So, this means for the general case, the assumption, the h of r multiplied by sin rwt cannot be a solution, okay. Means velocity can be out of phase with delta p, okay. Delta p may be moving, but velocity will have its own phase difference, okay. So, that is the what it means. So, now how do you go about solving this problem? So, you realize the problem is coming because when I am doing the derivative with respect to time, this guy is behaving nicely, sine, this is giving sine, but when I differentiate with respect to time, I get cosine, okay. So, I want to get the same function. If I get the same function when I differentiate with respect to the variable, then I will be able to cancel off all the terms, correct. So, what is the function which on differentiation gives me back the same function? Which function on differentiation gives me back the same function? Sine on differentiation gives me cosine, cosine gives me minus sine. So, which function gives me the same function? The exponential function e power x. E power x gives me back e power x on differentiation, okay. So, what I can do is I can therefore, so derivative of t e power t is e power t, correct. So, what I like to do is recognize that e power I r w t is cosine r w t plus I sin r w t. Cos theta is, I mean e power I theta is cos theta plus I sin theta, okay. So, I am just saying e power I r w t is cos plus I sin. Now, I am going to go back here and say, look, let me solve this problem. Let me solve the problem by dt equals e power I r w t duz by dt is, I am going to replace the sign by rw t plus 1 by r d by dr of r du by dr. Okay. So, in the same problem which I had, instead of sine, I've just put the exponential function. Now, the idea is, I have this is, everything was real here, but what I've done when I'm bringing it into this exponential form is, I have this imaginary number I, square root of minus 1. Okay. So, the solution for this will clearly be complex. It will have a real part, it will have an imaginary part. So, we are going to solve this equation. The idea is, I can seek the solution as e power I rwt multiplied by a function of r, okay, and then when I substitute it, the exponential term will cancel and I will get back my ODE in r. But what I have to remember is that my solution will have a real part and an imaginary part. Which part am I interested in? I am interested in the imaginary part, because the sign comes from the imaginary part. So, our strategy is to solve this equation in the complex domain, get a solution which will have a real part and an imaginary part, and find the imaginary part of that solution. That will give me the solution to what I am interested in here, this problem. Okay. So, I am going to do one thing. I am going to put some star here, because this is not the same as the uz. So, uz star has to is when I have the e power I rwt as a non-homogeneity, to differentiate it from this thing, and the uz is the imaginary part of uz star of t. Okay. So, clearly uz star is a complex domain function, a function in a complex domain function, and uz, okay, because my non-homogeneity now is complex. But the advantage is, I can now say I will seek my solution as uz star of r comma t as e power I rwt multiplied by h of r. Okay, time dependent part multiplied by a space dependent part. Okay, that is what I got, e power I rwt multiplied by h of r, and now I substitute this back inside here. When I substitute this back inside here, I will get on the left hand side I rw, okay, differentiating with respect to time, times h of r equals e power I rwt, the non-homogeneity as it is, plus 1 by r d by dr of r dh by dr times e power I rwt. Okay. So, now e power I rwt is coming in all the terms, and that cannot be 0. So, I can cancel it off. Okay. I am missing an e power I rwt here. When I differentiate it, e power mx is m e power mx. So, that is what I get. Okay. So, this is e power I rwt here. So, this e power I exponential term cancels off, and now I have an ODE in R. Only thing is, it is now in the complex domain. Okay, but now it is an ODE. That is a good thing. So, I had a PDE which was in R and T, which was real, but I have an ODE in complex. I do not know which is the more difficult problem, but we will do this. Clearly, this must be an easier problem, otherwise I would not have done this, right. So, to summarize what I have said, I wanted to solve the problem for the general Strouhal number, where the velocity does not have to be in phase with the pressure, okay. And mathematically I wanted to make sure that the exponential, the time dependent term is same in all the terms, so that I could cancel it off. So I went to exponential, okay, and in that process I had to get the complex function e power I r w t. Now, so the ODE for r is 1 by r d by dr of r dh by dr, okay. I am writing this on the left hand side. I am going to move this to the other side and move the left hand side to the right hand side, okay. I am doing lots of stuff here. So, minus I r w h equals h minus 1, okay. So, I moved this 1 here, I moved this left hand side term here, and this is what I am getting. And what will be the boundary conditions which I have to satisfy? H at r equal to 1, the wall must be 0, because only if capital H is 0, the no slip boundary condition will be satisfied, okay. And I also want to make sure that the solution is bounded. So, H must be bounded. H is at r equal to 0 is bounded. So, this is a second order equation. I have two conditions. So, now clearly this equation is a linear equation, okay, H, and this is the non-homogeneity, okay. Boundary conditions are homogeneous, and I can solve this problem by looking at the solution the usual way, looking at the particular solution and looking at the complementary function, okay. The complementary function will satisfy the homogeneous equation and the particular solution will satisfy the differential equation, okay, what you have done in your math course earlier. So, the solution H of the particular solution H is HP plus H complementary. This is the particular solution and this is the complementary solution or complementary function, whatever they call it. So, look at it, because it's a very simple equation. HP turns out to be the particular solution has to satisfy this differential equation, okay. Supposing I look for a solution which is independent of r, this goes to 0, the particular solution HP will be 1 divided by IRW, because I put 1 divided by IRW, I will get minus 1 minus 1, the equation is satisfied, okay. So, this particular thing satisfies that equation. I do not like to have the I at the bottom, so I am going to multiply by I in the numerator and denominator, and I will get minus I by RW. So, this is my particular solution, okay. Basically, the particular solution satisfies my differential equation. So, just substitute this thing minus I by RW here for H, I will get minus, is right? Yeah, minus, yeah, this is perfect, okay. So, now I need to find the complementary function which satisfies the homogeneous equation, okay. So, HC satisfies homogeneous equation. What is that? 1 by r, I am going to expand that out, man. 1 by r, okay, let me do it step by step. Minus IRWH C equal to 0, okay. I am going to make, I am going to expand this by product rule. So, I get d square HC by dr squared plus 1 by r dhc by dr. This is just the product rule. okay, and this one I am going to write it as plus RW divided by I times HC equal to 0. I multiplied this by numerator and denominator by I, okay, and this gives me this form. I wanted I in the numerator there, I want I in the denominator here, so you are confused. The reason is I want to have plus sign here, because now this falls under a classical Bessel function. The solution to this with a plus sign I know is my Bessel function J0 and Y0, okay. The reason why I now have the I at the bottom is because I wanted the plus sign, okay. So the solution to this is, this HC is of the form A J0 square root of RW by I into R plus B Y0 square root of RW by I multiplied by R. So the motivation for doing this conversion is so that I can get the solution directly. Now, I mean, just for the sake of information, I think what you need to know is there is this handbook, Abramovich and Stegan. So when you are dealing with different kinds of coordinate systems, okay, you will have different kind of partial differential equations, ODEs, okay, and the solutions to this sometimes you get, they are all classical. You have Laguerre functions, Legendre polynomials, you have Chebyshev polynomials. So all kinds of different solutions will be there. So this particular book is a mathematical handbook, okay, which contains all of this. It's not that you are expected to remember all of this, but if you come up in your life and you have to deal with solving an equation, then you may want to refer to this, because the solution to your equation will be here, okay. So I am just telling you that this book is basically for cylindrical coordinates, for spherical coordinates, for other coordinate systems. You have different kinds of ODs which you will encounter, and the solutions to those are already existing. So it's not that you have to wrestle with those equations and find solutions. The first thing you should do is look at this thing, because the solution may already be here. And so basically it's not that you have to remember all of this, okay. And of course today you have all your software tools, Mathematica and MATLAB and Python and all kinds of stuff. So I am sure most of these solutions are also there, okay. So the point is, you do not have to get intimidated by this. This is something like a sine and cosine which you have in Cartesian coordinates. In Cartesian coordinates, when you solve this homogeneous problem, you get sine theta cos theta. Only thing is, sine theta and cos theta you are comfortable with, because you have been doing trigonometry for the last so many years, okay. So just think of this as sine theta and cos theta in a different form, okay. Anyway, so this solution, I mean, it's not that I am remembering everything, but it's just that when you encounter equations of this kind, especially ODEs with variable coefficients, okay, because this 1 by r is the problem. It makes my coefficient variable. It's not constant coefficient. If it's constant coefficient, I'll get sine theta cos theta, but sometimes the variable could be r, could be theta. Then you have different solutions. Anyway, so this is the Bible or the Quran or the Gita you have to go to find solutions, okay. And otherwise you can go to internet, but don't come to me, okay. So now this is the solution, great. So I have the homogeneous solution. This goes to 0 because y0 is unbounded, okay, and you don't want the velocity to shoot off to infinity, right. So that goes off, and therefore your solution H is going to be the particular solution, which is minus I divided by RW plus the homogeneous solution, which is A times J0 times square root of Rw by I times R. This is my H, and I need to find this A, and I need to get the A by using the boundary conditions. Okay, at R equal to 1, H must be 0. So, at R equals 1, H equals 0. This implies H is 0, put small r equal to 1, I get I by Rw divided by J0 of square root of Rw by I. This is A. Okay. So, I found my arbitrary constant A, which came by using the boundary condition. Okay. There were two constants, boundedness made this 0, and the other one was found by using the wall boundary condition. A is known. Now I can substitute this A back inside here. You can see that the solution is now complex. So, what is U? Z star of R comma T, it is e power I RWT times H of R, and H of R is also complex. E power I RWT is complex because I changed the non-homogeneity to e power I RWT. This and H of R, you can see, is already complex, lots of i's sticking all over the place. Okay. So, now you have a complex function, and you have to calculate what the imaginary part is. Okay. So, I am going to leave it at that. So, one of the things which I am going to tell you is, so you can do most of these calculations quite elegantly and quite effectively in these software packages like Mathematica. So, one of these days, maybe next week, we will have a session where we will introduce you to some of these tools, so that you can get comfortable with using this. Okay. At the end of the day, the expression is one thing, you also want to be able to visualize what you have seen graphically, right. So, you are interested in plotting uz as a function of r for different times to see how the periodicity is, or as a function of time for different hours, whatever. So, all these software packages make it very easy for you to do, and you have to get comfortable with them so that you can analyze the results. So, that is something. Once you get the solution, this solution you can see clearly will be having some combination of cosine and sine, because this is going to give me cos and sine, this will have a real part, imaginary part. So, all this you will have two contributions coming. What I expect is that in the limit of low Rw, the velocity will have to be in phase with delta p. That is what I already saw. Okay. So, when you do a problem, when you do a calculation, when you find a solution, you have to make sure that the solution is correct, right, or at least it is not wrong. So, after you get the general solution, you have to put the limit of Rw going to 0 in this general solution and see if you get an in phase solution which you got earlier. I mean, that is basically what you have to do. You always cross check any result, whether it comes from an analytical solution, whether it comes from a numerical solution. You have to make sure that that is something which you can cross check with, validate with, so that you are confident that your code is correct, your analysis is correct. Okay. So, that is basically what you have to do. So, in the limit, I am going to say so this is the general solution. Velocity is not in phase with delta p. That is the first thing. Okay. As Rw tends to 0, velocity and delta p must be in phase. So, we use this to check if our solution is correct. So, if they are in phase does not mean your solution is correct, but if they are out of phase at low RW, then your solution is wrong, that is for sure. Okay. This can be used to check your result, and this is especially true today because I mean there are so many software packages available. I mean ComSol, Fluent, ANSYS, so many solution software packages, definitely you are going to get some result, but more important thing is to find out if the result that the package is giving is indeed correct. Okay. That is where your intelligence, your smartness comes in. Otherwise, you go and say you show some result, you get a beautiful color picture, and somebody is going to observe and say, look, this is violating some fundamental law. Then I mean, if you have not thought about it, you got a problem. Okay. So, please, especially those of you who are going to use commercial software packages, and be very, very careful. If you are writing your own code, you have to be very careful. Okay. Yeah. So, so we will have 1 or 2 sessions. So, to get you comfortable with Mathematica, I think you already done a course on process analysis and simulation. So, but we will do it with this in mind. See, I think the logic in every step is what you have to understand, rather than just follow the steps blindly. I am going to stop right now for as far as 1D flows are concerned, and I want to move to 2D flows. Okay. And maybe we have done a whole bunch of problems with 1D flows, time dependent, steady state, in cylindrical geometry and all that. So, let us go to a 2D flow system, 2D flows. Okay. And what do I mean by this? There are 2 non-zero velocity components. That is what I mean. Again, what we will do is we will start with the Cartesian coordinate, then move to maybe cylindrical and spherical and all that. Okay. So, just to lay out the structure so that you can understand things easily, and I think one point you have to understand is that when you go from one geometry to another, things are only getting mathematically complicated. I mean, instead of sine you get Bessel's, you may get Legendre polynomials for spherical. Okay. But the approach is the same. So, if you understand the approach properly in Cartesian coordinates, you should be in a position to apply it to any other coordinate system. Okay. I mean, if it is the same problem, if it is a reaction, first order reaction in a rectangular slab, same principles for rectangular first order reaction in a cylinder or in a sphere. Okay. But if the physics is different, then maybe you need to come up with something else. Okay. So, for example, in this problem, low RW physics was slightly different from general RW, we use slightly different method. So, mathematically complicating when you go from one coordinate system to another coordinate system should not really make you panic. You should be saying, look, I know how to solve this problem in this coordinate system. I mean, I will follow the same methods with modifications for my coordinate system. Okay, that much confidence you should have. So, again we will start with rectangular Cartesian coordinates, then go to other things. Let us consider the case where Vx is equal to x. What is this? This is the x component of velocity. I am saying I have a velocity field where the x component of velocity is given as x. At every position x, the velocity is Vx is x, the x component of velocity is x. So, clearly I want to make sure that my velocity field satisfies the equation of continuity, correct. So, this must satisfy the equation of continuity, and in the rectangular coordinate system dvx by dx plus dvy by dy must be equal to 0. So, what is dvx by dx? Dvx by dx is 1. So, this implies dvy by dy equals minus 1, or vy is equal to minus y plus some constant which could be a function of x, okay, but depending on the boundary condition only I will get. So, I will just leave it right now, we will just say that the constant is 0, okay. So, idea is a velocity field Vy, okay, if this is the x component of velocity field, the y component of velocity is going to be given by this. All I have done is made sure that I have my equation of continuity is satisfied. So, I have two components of velocity now, Vx and Vy. So, that is what I meant by saying a 2D. So far we only looked at one velocity component, all other velocity components were 0, okay. If I have this xy coordinate system, at every point here Vx is x, Vy is minus y. So, this is the x component of velocity is positive, y component of velocity is negative. So, what is the resultant going to be? Resultant is going to be at some angle, right. This is Vx, this is Vy, okay. So, you can actually calculate the direction of the velocity arrows at all the points you have. At this point again positive, negative, something like this, and as we get closer to the x axis y is 0, as y is 0 that means closer to the x axis y is 0. So, Vy is 0, there is no y component of velocity, velocity is only horizontal. So, here the velocity is going to be horizontal, agreed, and along the y axis x is 0, and you have no horizontal component of velocity, only the y component of velocity is there, and that is negative. Okay. So, that is what you get. So, I am trying to plot how the velocity is going to look. So, at different points you will have different components, but this is how it shapes. Closer to this it will be vertical, so at every point you are going to have so if you want to connect all the points, okay, suppose the particle here it is going to go in some direction, the particle is going to go along this kind of a trajectory. These are the trajectories you are going to see. Yeah, there is one trajectory like this. Okay. What have I drawn? I have drawn curves, and at each point on this curve the velocity is tangential. Velocity is tangential to this curve at every point, okay. So, if I come here, I may draw the tangent, that is the net velocity, it has an x component and this has a y component. Now, these curves that I have drawn, these are called streamlines, okay. And the definition, and I want to be very clear, this concept of streamlines is basically used only for 2-dimensional flows, okay, you cannot use it for 3D flows, okay. So, remember that. So, streamlines and okay, stream function especially, okay. So, now what I am going to say is on the streamline, a stream function is defined, and this is only for 2D flows. This is denoted by this Greek letter psi, okay. This is psi, and this is the stream function, and on the streamline psi this is equal to constant, okay. You can think of these streamlines as these magnetic lines of force or electric lines of force which you had when you were doing a physics course, okay. So now the point is the stream function for 2D flows only, okay, and I think I should write this only very clearly here. Now, so if psi is constant along the curve, that means along the curve d psi is 0. There is no change in psi, okay, because that is how I have defined my stream function. I am looking at a function which does not change along the streamline, and clearly d psi is nothing but d psi by dx times dx plus d psi by dy times dy. This must be equal to 0. So, the change in psi along the curve is 0, and that is given by this, okay. Change with respect to x multiplied by dx when I go from one point to another on the curve. When I go from one point to another, there is a change in both x and y, and I am taking that into account. And I can rewrite this as dy by dx as dy by dx equals minus d psi by dx divided by d psi by dy. Is this correct? So, I moved it to the other side, I got a minus sign, minus d psi by dx by d psi by dy, okay. I am telling you that this dy by dx is nothing but the tangent, nothing but the direction of the tangent along the streamline, and I told you that the direction of the tangent must be the same as the velocity. On the streamline, the velocity is tangential to the streamline. So, this is the slope of the streamline, the velocity is tangential. If you do that, you will get this is Vy divided by Vx, okay. So, the first part is coming because of the definition that psi is constant. The second part is coming because I am telling you that along the line the velocity is tangential. So, this is the slope, and the net velocity, this is Vx, this is Vy, the direction is going to be, the tan theta is going to be given by Vy by Vx, okay. This is the slope of the streamline. So, now I can define Vy. How do you find this stream function minus d psi by dx and Vx as minus d psi by dy? All I am doing is saying Vx is d psi by dy, Vy is this. You have the flexibility to put the minus sign either here or here, that depends upon the sign convention, it does not matter, I have just chosen this, okay. So, I am just choosing this as my example. You may see some books, they will say Vy equal to plus and Vx is minus, that is also okay, it does not matter, okay. So, basically if I know what is Vy, okay, this is how my stream function is defined, and what we can do to find psi is we can integrate this out. Okay, Vy remember is, what was Vy? Minus y, is it? What did I find out? Vy? Vy was minus y. So, minus d psi by dx is equal to minus y. So, psi on integrating will give me yx plus some function of y. Okay. And what is d psi by dx? I am going to differentiate this thing. I am going to get d psi by dy, which is dx, which is equal to x, which is equal to y plus f dash of y. This is x. So, f dash of y equals 0. So, all I am doing is I am differentiating this with respect to y. D psi by dy is nothing but Vx, which is x. Differentiate this with respect to y, I get x, x cancels, f dash y equal to 0. So, f of y is a constant. Okay. So, you can see that the stream function x and y, this is nothing but xy equal to constant. Okay, stream function is constant, fy is constant. So, basically what you are going to get is a bunch of rectangular hyperbolas, xy equal to constant. Okay, these are my streamlines. Given by xy equals constant. What I want to do just before closing is trying to tell you what is the motivation for using this stream function formulation. So, when you are trying to solve two dimensional flows, you need to solve for two velocity components, okay, Vx, Vy, Vr, V theta, Vr, V phi, whatever it is. And you can use the equation of continuity and the two momentum equations to solve. So, I have basically three equations to solve for the pressure and the two velocity components. When you use the stream function, what we do is we eliminate, okay, the velocity and find the solution in terms of the stream function. We first find the stream function and then you use these definitions of Vx, Vy to find the velocity. So, it is like saying in mathematics you must have done, no, you have a system of equations, you have let us say two equations and two unknowns, you will eliminate one variable from the first equation, substitute it in the second equation and then solve. So, what stream function is doing is something similar. Rather than solve two equations in two unknowns, we will get a single equation for the stream function, which we will solve, and once I solve the stream function, I can get the velocity field. Okay. So, I mean that is the analogy you can think of. Rather than solve three equations in three unknowns or two equations in two unknowns, I am doing a manipulation to convert this to one equation and one unknown. The one equation could be stream function, okay, and then we proceed and find the solution for the stream function. Once I get the stream function, I can get the velocity field. So, 2D flows can be solved either in the primitive variable formulation. Primitive variable means u, v, w, p, or in the stream function formulation. So, 2D flows people will normally prefer to do in stream function because it is much more easy for you to do it, analytically you have only one variable to look for. If it is 3-dimensional flows, you can't use stream function anyway, then you have to go for primitive variable formulation. Okay, that is the general background. Now, we will proceed further with stream functions.